today I'm thrilled to say that I have a co-host, the one and only Ben Bradley.
Hello, Junaid.
Hello, Ben.
Oh, it's so great to be here. I'm excited. I've been waiting for this opportunity for my whole life. The moment has finally come, and it's thanks to one man and one man only. Junaid, thank you for having me.
It's my pleasure. It's my pleasure. Now, today, me and Ben have the pleasure of speaking to Associate Professor Daniele Dorigoni. How are you doing today, Dan?
I'm doing very well. Thank you so much. It's a great idea what you're doing right here, and thank you for inviting me.
So, you do research in quantum field theory, right?
I do. A little bit of quantum field theory, a little bit of string theory.
Ooh. Could you explain to us in year 2 terms?
So what you're saying is no equations. I shouldn't be writing anything. Very good. So quantum field theory and string theory are... Quantum field theory, okay. Quantum field theory works in the sense that it is really up to, like, now, the best description that we have of the real world. What happens is that people got really bored and they didn't know what we were made of, and they started literally smashing stuff together. You take a proton, you smash it with another proton, and you just look what's coming out. Quantum field theory is the best mathematical framework that actually tells you what is coming out. String theory, on the other hand, is beautiful. I'm in the maths department, so I'm very happy with discussing stuff that has nothing to do with the real world. String theory is, if you wish, an extension, in a certain sense, of quantum field theory. It kind of contains inside quantum field theory, but it's never been, nor I believe it will ever be, verified experimentally. For sure, in the period where I will be alive, it will not be experimentally verified. But it's a beautiful mathematical framework. But quantum field theory, to be a little bit more precise, is a way to describe what are called quantum fields. So you like to think about, like, particles as little balls that are floating in space. However, a better way to think about it is that the whole space is permeated by these quantum fields. And a quantum field can describe all the different type of particles. And the vacuum of quantum field theory, what you would expect to be empty space, well, it's not really empty. Because of quantum fluctuations, I'm sure you've heard the Heisenberg uncertainty principle. It tells you that actually particle can pop out of the vacuum and then disappear out of the vacuum. And the way to describe it is via quantum field theory. So you should think really these fields as some sort of, like, sheet permeating the whole of space-time, and some bubbles pop out of this sheet and then disappear. And these bubbles of quantum fields are particles. No equations.
So do you mean that, like, with quantum fields you can have sort of particles coming out of nothing?
Absolutely, yeah. So you can actually do certain experiments to really see these kind of behaviors. So usually, as I was saying, the kind of experiments that we're doing are, well, not me personally, I've never done it. Actually, my background is physics. So although I'm in the maths department, I studied undergrad physics. First 3 years I had to do labs, which I hated with a burning passion, and this is why I also decided to move to theoretical physics, no labs. But people who do experiments, what they do, they scatter particles. So you produce protons, electrons, various type of particles, and you smash them together. Now, because of these quantum fields, you have certain uncertainty behind. You're not 100% sure of what's going to come out. You know that there's going to be certain processes with certain probabilities. And so if you really think about this, some of these particles are generated out of, well, not really nothing, from energy. So, E equal to mc squared. So I lied, I actually said an equation now. But you know that energy is equal to mass. So when you scatter particles together, you're putting a lot of energy together that can be transformed in different type of particles. So really they're generated out of these quantum fields from nothing, but actually from energy. Yeah.
I see.
Yeah, so is all this kind of a new way of looking at stuff and describing stuff that can't be explained with other theories and things?
Yeah. So people have tried to come up with alternatives to quantum field theory. And as I was saying, so far, quantum field theory, in particular what is called the standard model of particle physics, is a quantum field theory describing all of the known interactions that we know in the real world: electromagnetic, nuclear forces, what is called weak force, strong force. Gravity is a little bit on the side, so let me get back to a second. But all of the particles and all of the forces of our universe are described by this unified theory. And it produces beautiful predictions that are matched by experiments. However, we also know that this cannot be the ultimate theory to describe everything. For example, gravity is not really part of the whole thing. Gravity, we still think of it as, in a certain sense, a classical theory. All of these particles are moving into space-time, but space-time is fixed. However, if you think about what I was saying before, that particles can come out of the vacuum and so on, one would also like to describe space-time in this sort of bubbly way, in a sort of quantum way. So far, we do not have a quantum theory of gravity. So, originally string theory came out as a way of describing particle spectra, the experiments, and soon it was realized that it was not working. And people moved on to what is called now quantum chromodynamics, the theory of strong interaction that was working better. However, then people realized that actually string theory is one of the possible frameworks that will give you a sort of unified theory of quantum fields and gravity. However, it also contains a lot of extra stuff, and as I said before, as a mathematical theory, I love it. If you really want to talk about the real world, not so much, because usually these string theories are containing a lot of different particles, which we have not seen in nature, so we know that probably this is not the right way of thinking about that. But as you were asking, this quantum field theory on its own is a perfectly good mathematical framework that describes everything we have seen so far in LHC, for example, this Large Hadron Collider at Geneva, but it's still missing a lot of stuff. For example, we don't quite know a description of dark matter, dark energy. As soon as you start really thinking about the cosmos, we know very little. When we think about the extremely small scattering these particles, we know a little bit more, but also we don't know everything there is to know. So you might ask, well, what does it happen if I keep on probing shorter and shorter distances? Well, first of all, we don't have a lab that does that. I don't think it's ever going to be built. You see, of course, I would love to build a gigantic lab that can scatter particles super fast. The problem is that you have to make an argument with people who are going to give you the money. And the argument is, well, let's see what happens. It's not a good argument. So I'm afraid there's going to be a little bit of time before they're going to build some bigger machine. But yeah, basically the questions that we're still left to answer is what happens on the extremely small and on the extremely large scale. Yeah. So there is still work for you guys.
It's kind of a field that I guess there's a lot to do. It's really exciting to see what we might find out and what we might discover in the next few decades and centuries.
Yeah, absolutely. Yeah. There is a little bit of course, there's always trends in theoretical physics, as in many other disciplines. So right now, some big trends are on quantum computing. So quantum computing is, in a certain sense, a follow-up of quantum mechanics. You don't need to go all the way to quantum field theory. You put a lot of different quantum mechanical systems together, and then you think, oh, well, I mean, there's nothing really more I can do. But actually now we're really getting to hardwares that they can really do these quantum simulations in some beautiful way. And one of the beauties over there is that by playing with the rules of quantum mechanics, you can achieve stuff that you cannot do on classical computers. So there was some big claim by Google that they reached what is called quantum supremacy. There's a lot of cool names in this kind of world, which means they reached a state of the art for quantum computers that you would never be able to achieve with a classical computer. However, then, IBM said, well, not quite, guys. You could have done the same with some medium-sized town capacity of storage. And all right, yes. But now there is a little bit of shift. There is a bit of frustration in a certain sense from the particle physics point of view, because as you were asking before, this theory works well, yes. Do we know of any experiment that doesn't quite match? Well, not really. We don't really know what else to look for. We are trying to come up with different type of theories which incorporate the standard model because we know it works well, and they would give some predictability. But so far there is a bit of frustration just because labs have shown that the standard model works beautifully well. That's great, but we also like to have some tension. Otherwise, like, you put down your pen and you've done everything there is to do in life. So far, people have been moving a little bit on cosmology. There's a big revival, and quantum computers is the other big topic at the minute. Yeah.
You need some drama in your life.
Absolutely. So, for example, there was this, when they announced the discovery of the Higgs boson, it was a beautiful scientific achievement, but basically nobody was surprised that was, like, we knew that the theory was very consistent, it had to be there. It would have been so much better. In hindsight, it would have been so much better not to find it. And then I was like, oh my God, then I didn't understand anything. I should do something completely different. But so far, everything the standard model is telling us has been verified experimentally. There are still, as I was saying, some tensions, but they're not massive tensions. For example, if you think about it, back in the days when people didn't even know quantum mechanics, they thought that, like, electrons, they're little balls going around. And then they were doing these double slit experiments. And then over there was a big tension. You're like, oh, the electron is either going left or right. Well, actually, not quite. It's behaving like a wave. And so that was really, like, some change on paradigms of thinking. We don't have this right now. But it's also, I should say, it's been a success of modern theoretical physics getting to this point. So at the beginning, literally, people were smashing stuff together and try to come up with arguments for why they were observing what they were observing. So it's really like, going in the dark with a little lantern. And now we have one of the best achievements of theoretical physics. We know it's not the end answer, but also we don't have this massive drama in our lives.
That's really cool. I mean, Junaid, you're a maths and physics student. I study pure maths, just maths. So kind of my stance on this is probably a bit different to yours, Junaid. But I guess it's quite interesting how the theoretical and the practical sides kind of interlock and kind of overlap with each other. And sometimes, as you say, there's kind of things that don't line up that means, well, this thing that we've actually observed doesn't match the theory we've got.
Yeah.
And I guess that's kind of a really interesting and really crucial thing to a lot of the development of the theory, particularly with things like, as you say, quantum and things. That's, I mean, over the last 100 years, that has developed so much from almost nothing, and it's so exciting to think about kind of what might be in store for the next 100 years.
Absolutely. Yeah. But also, in recent times, there's been quite a lot of interchange of ideas between pure maths and more theoretical physics. Just because you don't have some experimental verifications of many theories doesn't mean that they don't teach us anything. So in particular, the other big area of my research has to do with connections between string theory and number theory as a way of generating, like, really one of the things that as a mathematician, if you are a proper mathematician like you are, then you like proofs.
I feel targeted.
No, well, from my physics side, if instead I'm seeing 100 examples and they follow my pattern, then I declare this a victory and I declare it a physicist theorem. But of course, a mathematician would really like to prove it from, like, first principles. But a lot of these theories, although they don't have any physical verification, they actually give you ideas that then you can try to prove in maths for number theory. So there's a lot of interchange. That's just one topic. There's a lot of other stuff going on in connection between quantum field theory and geometry. And there's been really a revival of the idea of using theoretical physics, not just as a framework to, like, explain experiments, but as a framework to give you idea for which you can actually do mathematical proofs of interest to pure mathematicians, which I also found it very fascinating.
Yeah, I wouldn't have thought that there'd be any sort of practical, like, physical uses for, say, number theory, having started studying it this year. Yeah, as interesting as it is. But no, actually, I think that is very cool. Like, I would not have thought it'd have real world applications at all.
It's fascinating the way that, like, certain topics of pure mathematics are kind of things that are entirely in your own head and they don't really exist in the real world. Talking about, like, infinite dimensional spaces and things, it's like you cannot actually comprehend what that is, and yet things like that have fundamental kind of repercussions on the physical world and how we can understand it.
We love those kind of spaces. Those are the spaces for quantum mechanics. So, yeah.
Yeah, that's great. It's really exciting to kind of do research, because often research is kind of done for research's sake, and then it's only years, decades later that we find out, oh, this has an application.
Yeah. For example, going back to the point I was making before about these big machineries that are needed for experiments. Sure, from our point of view, of course, the end game is trying to discover new physics. However, in the process, even just from the technological point of view, last time they built CERN, they invented the internet. Oh, we're kind of happy with the internet. Like, it's a great byproduct. But like, in terms of using science, pure maths or like physics as a way of pushing like knowledge, and okay, it forces you to actually achieve little goals that maybe is not what you want to do on the longer run, but still they're like developing, say, pure math, physics, technology. Those are excellent stuff. Of course, like being in the maths department is a little bit more research for research's sake, but this sort of seeding of ideas between different worlds is working really well. Yeah.
Yeah, you mentioned like quantum computing as well as kind of, I guess, a whole another branch of science that is now coming into kind of being linked together with these mathematical ideas and these kind of physical concepts, that you've got all the computer scientists saying, hello, let's have a talk about all this as well. And I guess that's super exciting to see where that can take you, and that's kind of a whole new branch of things.
Absolutely. There's already, it's actually insane, the amount of, if you wish, programs that we have for quantum computers. It's already insanely big compared to actually how good our quantum computers are. So that's a setup where people knew the rule of the games. They are the rules of quantum mechanics. The whole creativity is how you put them together to come up with new algorithms that you couldn't do in a normal computer. Let me give you a concrete example. Whenever we pay on the internet, we use this RSA cryptographic algorithm, public-private key. This relies crucially on the fact that if I give you a big number, it's very easy to know that it's not prime. But if I ask you, okay, it's the product of two numbers, can you tell me these numbers? The answer is, well, no. It's going to take me a long time. Quantum computers do that in a short time. However, you shouldn't be scared, because we don't have a computer yet that actually can run it live by tracking your Amazon transaction and cracking your codes. However, this is one of the cases where we knew the rules. People are very creative. They put the rule together and it came up with a lot of new algorithms. The problem is that technology is a little bit behind. One of the biggest issues there, which is of course just a hardware issue, is the fact that the real world doesn't really want to be quantum. Every time you have a little bit of interactions with the environment, being that even just some thermal fluctuation, like you have the air which is moving a little bit, in general it destroys entanglement. And entanglement is the key feature of this quantum computer, what Einstein was calling a spooky action at a distance. But this is a hardware problem. How can you actually come up with a hardware that survives long enough for you to run your simulation, to run your quantum algorithm before the whole thing explodes? Doesn't really explode, but you get my drift, yeah. Before it actually disappears and is not quantum anymore. So we are at that point where really we need our engineering friends to do a little bit better and come up with a better quantum computer. Google and IBM, they're throwing stupid money at quantum computer because they know they're going to be the big breakthrough. Yeah, they're getting there, but the technologies are still a little bit behind our computers, tabletop computers. Yeah.
This is why I think theory is king. Ditch for labs, switch for maths and physics. Don't worry about real world applications. Just embrace the theoretical algorithms and all is good.
As a mathematician, I'm loving what I'm hearing right now. that's music to my ears today.
Good to hear.
So all the maths talk, all the maths people I interact with have just been rubbing off on me too much.
That's not a bad thing. That's not a bad thing. If anything, it's an excellent thing. It's going to change your life for the better, Junaid.
Oh, of course you'd say that, though.
Of course I'd say that. Yeah. I'm not paid to advertise maths. I do it willingly. It's okay. It's all good.
Okay, so now I was thinking maybe going for a slight change in topic. Maybe, Daniele, maybe you could tell us a bit about the sort of day-to-day kind of work you do in your research.
Very good, yeah. well, when I'm not teaching, which is unfortunately during term time is most of my time, it's a little bit like, it varies a lot. So there's a lot of social part of research. Of course, you can just go to your office and do whatever you want to do without interacting with anyone. However, there is a huge pool of people, open sources. I'm not sure if you've ever heard this website called The Archive, literally, where there's an open source. You can put all of your papers there. They're not necessarily peer reviewed, so take them like, with a little bit of salt. But it's a great way to see what people are doing. And by discussing with other people, you can actually generate new idea. Like, I'm an expert on this topic, you're an expert on this other topic, put together, and we try to come up with like some new ideas. So then there is the first stage where everyone is very excited. Oh yeah, so we have this new idea, let's try to like track it on. And then usually at that point, you try to research a little bit like what has been done in the literature. So that is a big change between, let's say, university studies and research. I love the university because all of your knowledge is in a book, is in the lecture notes, it has already been done. Research is hard because you don't know where you're going with your thought. Like, with experience, of course, you kind of know if what you're thinking is feasible or not, but still you don't know the end result. It might be that what the theorem you're trying to prove is just false. And then you're spending like, months and months trying to prove the contrary. So at the beginning, you try to see a little bit what has been done by other people. So you research a little bit the literature. And then after a while, you realize, okay, yeah, I just need to sit there and do my own calculations. So I try to do a sort of hybrid approach. As I was saying before, I'm not a mathematician, so I'm very happy with generating a huge list of examples, not necessarily like numerical simulations. I've done some numerical simulations in the past, like pictures of solitary waves, some sort of solitons object, which are called beautiful type of object, vortices, monopoles. And these are kind of stuff that you can simulate with a computer. However, most of my cases now are analytical studies, but I can generate a lot of examples and see if from this finite number of examples, I can spot the generic pattern. In many cases, it's literally patterns on numbers. And now I can promote one of my favorite websites on the whole world, and it's called the Online Encyclopedia of Integer Sequences.
Love the OEIS.
You go there, you put a bunch of numbers, and of course, these are the numbers of this and that sequence. And it's great, because sometimes from my examples, I don't know what these numbers are, you put them there, and you spot, of course, these are Fibonacci number or whatever. So there is a sort of experimental part, if you wish, although an experimentalist would like yell at me, because this is not really experiment. And then there's also, I should also be honest, so it's not all like, oh yes, you always discover new stuff. There is also a lot of frustration at the times, because you have all the pieces of the puzzle, you keep on staring at them for days and days and days, and you don't see how they fit together. And especially as a PhD student, you need to have a little bit of resilience, because it's not always that your research goes well. Like, it could really be that you get stuck, because maybe the idea was too ambitious, or maybe what you're trying to do just doesn't work. So then with experience, you realize when is the time to actually, okay, yeah, let me put this on a side. And it's also why it's really good to have, I'm blessed to have a lot of collaborators that are extremely good, so much better than me with a computer, so they can really help you out. They can produce more data for me. I can bring them my frustration and say, oh no, but we should try to do this and that. So the social part is extremely useful. And this is basically what I do when I research. I go to my office, I stare at my beautiful number for a couple of hours, and I just try to do something with that. Yeah.
That sounds quite nice. I'm glad to hear about the sort of social aspect in particular, because I guess with sort of physics research, there's the kind of idea of like mad geniuses just like bashing on a whiteboard on their own. Like chalkboard, yeah. Either or, keep your pick.
If you're that obsessed, it's got to be a chalkboard.
Yeah, okay.
I still have a blackboard in my office. I'm very glad of that. Yeah, not a whiteboard. No, the social part is extremely useful. Then, of course, at a certain point, there is also the social part of presenting your findings at a workshop and a conference. And like, at that point, you're also a little bit proud of what you've been doing. Look, I have put all of this stuff together and I generated some new knowledge. Let me tell you about this. And then at that point, there is also another part of the social aspect, because, as I was saying, there are trends. So although you might be very proud of what you have done, it might be that the bigger community doesn't particularly care. But it doesn't mean that you shouldn't be doing it, because as we were saying before, a lot of achievements were done, and in the past people, oh, this is useless. But then people later on realize, well, actually, no, this is not useless, so we can actually use it to do something else. So that part of presenting your work is also extremely useful. You're getting feedback from the community. You are getting a little bit of pride in presenting what you've done, which I think it's also good. And in terms of PhD students doing that, that is extremely useful, because when you're doing an undergrad, you're trying to get the core of your knowledge. And then as a PhD, you take a very specific topic and you become the expert of that topic. But then you're put in a position to face yourself with other PhDs who have been going to research in slightly different topics. So it broadens you a little bit the perspective. Yeah. Still very difficult, even later on, it's still very difficult to actually be following everything, just because you don't have enough hours in a day. But still, by having these sort of shorter aspects, you can get a little bit of an idea of what other people are doing. And then you realize, oh, actually, this stuff looks like something that I could be using. And then at that point, you can actually jump on the subject, you can actually read the literature and try to implement it in your research. So, yeah.
It's wonderful that there's that much research out there that you couldn't possibly keep up with it.
Yeah.
I think that's such a great thing that the scientific community has got that, and it's brilliant.
Just so on this archive, you can go there. You can go. It's for maths papers. They divided number theory, combinatorics, and so on. You can see that there's roughly 10 papers per day on all of these subjects. In theoretical physics, usually it's around 20. And it's great, as you were saying. I'm not 100% that all of these papers are, I don't want to say wrong, but also there's a lot of garbage out there. So there's a lot of noise as well, right? Because people, of course, they're trying to do research. And unfortunately, a big part of the academia later on is how productive you are. And if you are put under pressure of producing papers, then in many cases, something that maybe you would have put as an example, then you put it as a new paper. So there is a lot of noise. One of the good things of having an advisor is that an advisor has a bit more experience, so they can actually tell you, look, out of all these papers, pick this, and that. But all of the knowledge that you get out, it has increased dramatically. Back in the days, they didn't have this sort of internet repositories. So I still remember, I'm not super old, but I still remember in my department when I was a PhD student, you would have physical copies of preprints of papers. Because maybe I knew that you were in a different university, I would send you the physical copy and you would put it out there for people to read. And so this dissemination of knowledge was way slower. Right now, with the internet, you have a flux of papers, open access, that you can just read, and you can really see what everyone is doing constantly.
Yeah, the internet's done a lot for collaborative research, and that's a brilliant
Absolutely.
thing.
Yeah.
As we're saying, all these different kind of branches of science have to come together and have to work collaboratively. There's so many different perspectives that you have from different fields on particular topics, and that's really good.
Yeah, it must make it quite hard to know what to look at when you're doing literature reviews. So
Yeah, absolutely. That takes experience. Yeah, and luckily, I would say our world, both pure maths and theoretical physics, are small enough that at a certain point you actually kind of know who the good people are. It is also a little bit of a self-fulfilling prophecy. At a certain point, you tend to be biased towards newcomers. I don't know if you've heard of this recent progress in some number theory results. So we all know there's infinite number of primes, but there is this conjecture that there's infinite couples of twin primes that differ by 2 units. Very recently, and this is an open conjecture, people believe it to be true, they check it numerically, but this is not a proof. Very recently, there was a paper by this virtually unknown, I think it was a Chinese mathematician. And it was put out, but there is, as we were saying before, the flux of information on the internet is massive. However, it was picked up as probably not a fluke. And actually, although this person did not quite prove the statement, I think the statement that he proved was that there are infinite number of primes within distance, and I kid you not, 1 billion or something like that. However, this was a game changer. And this was coming from a virtually unknown person. So there is a little bit of bias of the community from newcomers or people who are not known. But whenever there are good results, the community is big enough that even if you're an unknown person, your work will still be read properly. And if there is something there, then oh my god, there is some new result. And people have actually started working on this stuff. It was also difficult because being part of the social group of people working on a certain subject, you also tend to use the same notation, the same machinery. This person from outside used some completely different type of math. So of course, all the experts in number theory, they were there okay, it's gonna take us a bit of time to actually understand if this is sensible or if this is nonsense. Yeah.
Yeah, it's I guess with academia there's always a fear about when you're trying to break into it, no one's gonna hear your voice or things like that. But I guess it's good to hear that people will recognize your work if you're...
At the beginning, there's a lot of possibilities. So as I was saying before, at the beginning you're gonna become an expert on some little area. And the communities over there are basically big families. So you go to workshops together and they're not massive. One of the good things is that we don't have this massive workshop for example, people doing med school are. Those are workshops with 2,000 people. How can you be heard over there if you're not already the super professor? Luckily for us, we have smaller workshops where basically everyone is an expert on what you're working on, maybe different facets, but still you're given the possibility, even as as a PhD student, as a postdoc, to actually present your work and be known by the smaller community. And then you have slightly bigger conferences, and when you get a little bit more advanced, they can actually be invited there to give plenary lectures on the bigger picture. But at the beginning, of course, it takes time to get to the bigger picture. At the beginning, you want to learn your problem and your problem alone to to every little detail, and then present your results to the smaller community. Yeah. No, it's of course, if you think about being a world recognized theoretical physicist, well, if you ask people around, who do they know? Einstein, Hawking, these are the few names of people they know. But even in theoretical physics, there are people who are extremely well known within the theoretical physics community. For example, if I said the name Witten, does it ring a bell? So he is possibly the greatest theoretical physicist alive, and he has a Fields Medal. So also the maths people kind of recognize this person worth. But it's very difficult to break, even if this person is super well known within theoretical physics. Outside, you're not of the same caliber, quote unquote. I mean, he's extremely good, but you're not at the same level of being known as Einstein or Hawking, just because there is a big threshold of being accessible to the wider community. Yeah.
Okay, thank you for that. I was thinking now we could maybe talk about how you got into academia and your reasons as to going into that as opposed to anything else.
Very good, very good. As I was saying, so my undergrad was in physics, and I always really liked, so when I was in high school, I was doing all of these maths and physics Olympiads sort of games. I really like the challenge of this little puzzle you put there, you have all the pieces of the puzzle, how do you put them together? And but I liked physics more than maths. I didn't like labs, that I didn't, but I liked the idea, as we were saying before, of coming up with some mathematical framework to describe the real world. So then in uni, I immediately switched to the theory side. So the way it worked was that the first 3 years were in common, so I had to do labs, and I hated them so much. I remember still one experiment, I still remember. So we were given something like 1,000 nails to measure, and then plot the histograms of measurement, just to show that in general, when you do some error, you're gonna get some Gaussian, some standard deviation. And of course, smart student knew that, and so you just fake the data. Of course, the professors were smarter than us, and they knew that we knew, so they would give you 2 different sets of nails with slightly different lengths. So you would actually get what is called a bimodal distribution. And I remember measuring nails and hating my life, and I said, okay, I want to do theory. So I switched then for the master in theoretical physics, which I loved immediately. So I really liked how we were putting together very abstract objects in pure maths with like, physical application, not really experiment, but like, a lot of beautiful objects. There's a lot of beautiful mathematically rich theories, quantum field theories, which are called supersymmetric field theories, string theory, and so on. And so I immediately decided I wanted to do a PhD. And as I said before, a PhD can be a little bit frustrating at times, just because like you don't really know if what you're doing is a waste of time, if you're ever gonna go like to the right result. And I got lucky enough, so it depends a lot also. There is a bit of luck involved, as everything in life. You can put as much effort as you want. You need to be lucky to have a good advisor who knows actually when to like pull the plug to a project, put you on something else. So I got really lucky. I got 2 really good advisors, and they helped me out. And then after that, I knew I wanted to do at least a postdoc. So I did my undergrad was in Italy, but then my PhD, I did it partly in Italy and partly in France. But the French system was very weird, and I really didn't want to stay there. I really liked it, but I found a postdoc in Cambridge, in the UK. So then I didn't leave the UK after that. And over there I got really lucky. There was, as I was saying before, the social component was extremely important. It was a really lucky period. We were something like 8 postdocs, all young kids, all they wanted to show like, that they were doing like cool stuff, and we will all interact together. So I was able to actually do quite some good work, go around, produce some papers, and then after that I kind of knew, yes, okay, I really like doing research, so I'll try to like continue. It's difficult because you have to move a little bit around. I was really lucky because basically I came to Cambridge, and then I think I did 1 year in Germany, and then I came back in here in Durham. So you need to change. Usually these few years of postdoc positions are a couple of years, and then you have to move. Honestly, if you want to have family, that's a little bit tricky. So there is not really a lot of help from that point of view. If you want to stay in a place, there are not a lot of possibilities. It's really meant to be as a sort of way of moving around until you get a permanent position. Yeah, which I understand it's a big barrier, because at a certain point people are like, you know what, I want to stay stable in some place. So that part is hard, I would say. You really need to love it. I do love research. I do love teaching. I would like to say a few things that do not quite work here in Durham University, but I'm not going to enter there. But I do love the teaching part. And you see, like, teaching gives you a possibility to explain things in the way you would have liked them to be told to you. So it kind of really helps. And I think actually the teaching I'm doing here, I'm very happy with. So I'm doing quantum computing, actually, so self-promoting for this term, which is a really nice module, because you get really to show students some cool stuff. But then, like, research-wise, it gets a bit tricky. So teaching takes time. Research also takes time, but in many cases, you need to sit there still thinking about a problem. As you were saying before, it's all in your head, right? You have to do these mental constructions, and if you need to, like, go and teach, go and do some tutorials, the mental construction collapses. So every time getting back there takes a bit of time. So finding a good balance, I think it's good. I did some teaching when I was a postdoc, just because, as I said, I really liked it. But as a postdoc, you are spending most of your time doing research. So doing a little bit of teaching, I actually liked it as a sort of break from the mental constructions. Yeah.
Yeah, it's a bit of variation, isn't it?
Yeah, absolutely.
I wanted to ask, kind of, because obviously you do a lot of research in these topics. I know Junaid and I both took the linear algebra module last year that you taught. That was one of my favourites. I'm not just saying that, it was...
That's because I'm here in the room with you.
Yeah, if Danielle was not here, then the truth would come out. But for now, it's my favourite. But all joking aside, like, what are the challenges you find in kind of getting a topic like that, which is so abstract and kind of such a theoretical thing, across to students who may not have seen stuff like that before, may not have seen, in that case, mathematics in that sort of way, in that sort of style?
Yeah. Good.
What are the challenges with that?
Good. Yeah. So there's various different ways of teaching it. So the way I try to teach it is precisely as I said, try to visualize many of the concepts. And this goes beyond linear algebra. I really believe, like you see, one of the big things of maths is that at a certain point we spot patterns. The things you see in linear algebra, in many cases you should spot, oh, this pattern is very similar to the other pattern I've seen in group theory. Or, for example, if you think about vectors, you say, oh, inner products that we have seen, oh, this is actually very similar to what I'm very familiar with in 3 dimensions. So one of the big things of mathematics is trying to see how all these seemingly different things actually fit together under the same umbrella. So I found it very useful to actually keep on reminding, well, actually, although I'm making this definition which looks very abstract, this is just the more general version of something that you've already seen and you're very familiar with. So, of course, you could teach it. So my undergrad, although it was in physics, it was taught by pure mathematicians. And some of them were great teachers, but you were given definition. And it was up to you to actually sit there after the lecture, like books and books and books, until you realize, oh, actually, I now understand this definition. I can visualize it in this way. So I found it very useful rather than immediately trying to grasp the big picture. I'm going to give you the big picture, but I'm going to just keep on reminding you that this big picture is just putting together a lot of stuff that you've already seen before. The hardest thing I would say of linear algebra is the sheer number of students. That is yeah. But and also I really like it as a module because I get to see like first year students. Like, it's your first experience after high school. And like in university, it's very scary at first because like, you're thrown in the water and you're told to swim. And it takes a little bit of time to getting used to. So I hope I was able to do a little bit of a job, like, to ease you into it.
Oh, absolutely. Yeah. I think it's really great to, particularly with something like that, to have kind of always in the back of your head kind of analogous 2-dimensional and 3-dimensional cases. But when you're talking about arbitrary numbers of dimensions and things that don't necessarily exist in the normal way, it's great to have that sort of thing to relate it back to.
Yeah, because then also in this way you're gonna start building confidence of you realizing patterns, and then once you start discussing this non-existent, well, everything is non-existent, but like, these vectors in 15 dimension and so on, we say, okay, although I cannot visualize it, I now have enough experience in understanding what are the general properties that even if I'm in 15 dimension with complex entries, I still know what I'm actually talking about. And then you see more abstract stuff. Now you're taking probably algebra 2 and so on, so you start seeing more abstract stuff, but you can still bring it back to more concrete things. And then your notion of being concrete evolves with time. Like next year, rings for you are going to be very concrete, although it's nothing that you can find in the real world. But yeah, it definitely helps breaking it down into smaller things that you can visualize, and then you start building from there. Then, like, you get more experience, you find it easier to visualize more and more abstract objects.
Yeah, I think having something real you can link things back to is just always much easier than just bombarding yourself with abstract theories one after another.
I don't know, I like the maths. I don't do none of this physics. It's the maths for me.
Wow, okay.
Doing experiments.
Shade.
No, just numbers, Junaid. All the numbers.
Okay, I think we can maybe start to wrap up there.
Yeah, I have one big question.
Sure.
I apologise to all the listeners who've been bombarded with the seriousness and the physics going on here. If you'll allow me to take it just a level even deeper, something even more important and academic. In 2 words, it's Fruity Fridays. Now, Daniel, I know you're kind of part of this movement, this recent movement that has started. Could you kind of give a little summary of what Fruity Fridays is for all the listeners?
Well, I think all credits goes to Ralph and Luca, who are 2 great students always sitting outside of my office. And they decided to make life in the department a little bit like nicer 1 day a week. And for this reason, we are wearing very fruity T-shirts or shirts on a Friday, just like, to lighten up the mood. And yesterday, one of my colleagues surprisingly brought a ukulele of his little daughter, and it's extremely good. So he started playing Somewhere Over the Rainbow on the ukulele, and everyone was like, merry and like cheerful with very colorful shirts. So I thought it was like a nice idea. I have to say, I really like how now the department is actually your department as well. I don't know if you had the pleasure of being in the old department. It was, let's say, not good. Now this is the department where we're all there, and I think it's really good to have a one day where you can actually like take it easy and enjoy each other's company.
Yeah, it's things like that that really contribute to the kind of collaborative and social aspect of academic departments, and kind of link back to all these things about research and help us all discover new stuff and kind of work together better.
Yeah, I think having like a sort of sense of community is very important in any work, really. It's gotten to a point now where if I wake up in the morning and I see Ben wearing like a Hawaiian shirt, I know,
it's Friday.
You can set your calendar by it.
I'll use your shirt you've got as like a basis for my understanding of time.
Yeah, that's all you need in life. Fruity shirt on a Friday, you're golden. You're golden.
Okay, well, I think that's everything, unless you have any closing remarks, anything you'd like to say, Daniele?
No, I think this is a great idea. I hope there are a few people listening online, and I think you should continue doing that. Yeah, there's more of us in the department. One of the good things, there's a lot of young people. So we are all very keen with research and teaching and getting to know you guys. So yeah, thank you so much for having me here.
Anytime. It'd be good to have you back. Well, that's all for this week. Thank you all for listening. I hope to welcome you back to another episode, hopefully with Ben along as a co-host.
I can't wait for the next one, Junaid. It'd be great to be back at some point.
Yeah, having someone else to talk to, converse with, I think I did a lot. I really enjoyed it compared to just coasting on my own.
Yeah, be great to be back again.
Okay, well, I'll see you all next week. Goodbye.